Hey guys, welcome back to the channel. Today we will be solving some more questions of vector space wherein we will be checking whether the given condition are vector spaces or not. For the first question we have a set which has the elements x1, x2 and x3 belonging to R cube, which means it's a three-dimensional condition. Okay. And the second condition is x1, x2 and x3 are rationals under usual addition and scalar multiplication. Okay, for doing so, before jumping to the vector addition, let's first focus on scalar multiplication. Okay. Okay, what do we mean by that? Scalar multiplication states that any real number which is alpha multiplied by the given vector should give a vector which should be belonging to the given vector. For the given question, let's take alpha as root 2 and let's take this vector as 1, 1 and 1. When we multiply, what we get is this vector which has the value root 2 and root 2. Now, since it's given in the question that x1, x2 and x3 are rationals, and in this condition these are not rationals, so our scalar multiplication condition is dissatisfied, and hence this equation here, this set is not a vector space. Now let's jump to the second question. So for the next question we have a set which has elements x1 and x2 belonging to R square, which means it's a two-dimensional set, and the condition here is x1 is twice the x2. So all of the sets of this V would look like 2x1, and here it will be it will look like 2x and x for all x belonging to real number. Okay, so first of all let's check the usual addition condition. Okay, now let's take two sets, namely a1 and b1 with the values 2a1 and 2a here 2b and b respectively. Now let's see what will happen if you just add these values. So upon adding a1 and b1, we will get 2a plus 2b, and here we will get a plus b. Simplifying this equation, we will get, let's take 2 outside of the bracket and a plus b. Here let's write a plus b as the same. Now let a plus b equals y. So upon doing so, what we will get is 2y and y. Now a1 plus b1 gives us 2y and y, which belongs to our condition. So hence the usual addition condition is satisfied. Now what about scalar multiplication? Okay, so for scalar multiplication, let us take alpha as 2 and we will take v as our set, which is a 2a and a respectively as given in the question. Now let's just multiply alpha and v. What we will get is 2 times 2a and a. The 2 will go inside of the bracket, 2a and 2a, it will become 4a and 2a. Now upon carefully looking at this also satisfied our condition which is given in the question. So is the scalar multiplication satisfied? Yes. Okay, what about the zero condition? Zero vector. What will happen if we just take all the values of v as 0? Is this satisfied? Yes, absolutely. You can say that this is twice of this. So since addition, usual addition and scalar multiplication as well as zero vector is satisfied, we need not define the other axioms conditions like distributivity, associativity, etc. Since it's given in the question that we have to prove under usual addition and scalar multiplication, so all that properties are already satisfied. So yes, we can say that this is a vector space over R. Let's see what the next question is. For the next question, we have a set V, which is a set of all real sequences with first term equal to 1. So this set looks like this. xn is a real sequence with x1 equals to 1 under component wise addition and scalar multiplication. Okay, let's solve this. Okay, so first of all, let us check the zero vector condition. Okay, so in terms of sequences, the zero vector looks like this: 0 0 0 and so on. Now since this has first element as 0 and we have been given that our question contains first element as 1. Okay, so for some examples, any sequence of this vector will look like this: 1 2 3 so on, 1 minus 2 minus 3 and so on. These are the example of what the sequence of this vector will look like. Okay, and so on. This is a real sequence with x1 equals to 1. Now since the zero vector condition should have first element as 0 and in our case we have first element as 1, so automatically this denies the zero vector condition and therefore this phenomena is not satisfied. Now let's check the scalar multiplication thing. Okay, let's take an alpha which belongs to a real number. Okay, and let's take a sequence of this vector as 1 x y z and so on. Let us multiply alpha with v. We will get alpha x y z and so on. Now since this set has first value as alpha and in our case we have first value as 1, this also automatically denies the condition and hence the multiplication, the scalar multiplication is also not satisfied and hence we can say that this set is not a vector space. So for the next question, we have been given that V is a set of real sequences with first term being equal to 0. What does that mean? It means that V is a set which has xn and xn belongs to a real sequence and x1 is 0. Some example of this set are 0, 1, 2, 3, so on. Okay, and 0, pi, 2 pi, and so on. These are some of the example of this set. So first of all, let us check the closed under addition. Let us take two sequences from this set such as 0, and let us name these sequences as A and B respectively. 0, x, y, z, and so on. 0, A, B, and C. Okay, upon adding this, what we will get is 0, x plus A, y plus B, etc., which still holds true for our condition because this has first element as 0, so it has passed the check. So that's why closed under addition is satisfied. Now what about closed under multiplication? For closed under multiplication, let us take alpha, which belongs to a real number, and let us take a sequence from the vector set as, let us say, k equals 0, 1, 2, 3, and so on. Upon multiplying this, we will get is alpha into k, that is 0, k1, k into 1, k into 2, etc. Since this satisfies our multiplication condition as well as the closed under addition, we can say that V is a vector space. Or all the other exams like distributivity or associativity need not to be clarified here, since we are working with real sequences which are usually vector spaces and being satisfied all the conditions except these two. So all the other conditions are need not to be clarified here. I hope you're getting the questions. Now let's jump to the next question. In this question, we have been given a set which has the following things: x, y, 2 belonging to R cube, which is a 3D vector having the third element always as 0. Okay, so for some example of these vectors are 1, 2, 2, 2, 3, 2, 4, 3, 2, etc., wherein x and y could be any real number. So let us directly jump to scalar multiplication. Okay, let us take alpha, which belongs to a real number, and let us take a sequence, a set from the given set as v equals 4 or x, y and 2. Upon multiplying, what we will get is alpha times v is alpha x, alpha y and 2 alpha. Now until and unless so we were talking about what will happen if we multiply alpha to the x, y and 2 respectively. Now after multiplying, what we have noticed here is the third element becomes 2 times alpha, which does not equals to 2, and therefore this condition does not satisfy the scalar multiplication, and hence this vector, this set is indeed not a vector space over R. For this question, we have a set W which has element A belonging to a 3 by 3 matrix, wherein A is a non-singular matrix under usual addition, scalar and scalar multiplication. First of all, what is a non-singular matrix? A matrix is a non-singular matrix when it is a square matrix, it has an inverse, and its determinant shouldn't be 0. Okay, so for solving this, first of all, let's see the usual addition. Okay, the vector addition. Okay, let us take two matrices which are inverse to each other. For example, let us take two matrices as I and I inverse. When we will add those, we will get a zero matrix. So since 0 has its determinant as 0, it is a singular matrix, and since it is given in the question itself that A should be non-singular matrix, this does not satisfy our usual addition condition. Additionally, let us take multiplication of scalar. Okay, let us take alpha, which belongs to a real number, as 0, and let us take any matrix, any 3 by 3 matrix, let us say I. When we multiply this, we get alpha into I, which is a 0 matrix. Now 0 matrix, since 0 matrix is a singular matrix, it has its determinant 0. This automatically dissatisfies our condition, and hence this set is not a vector space. For the final question of today's lecture, we have a set having the values of all the integers. For example, -3, -2, -1, 0, 1, 2, 3, 4 and so on. So first of all, let us check, is it closed under addition? Let us find out. Take any integers, for example -3 plus, let us take 2, it will give you -1, which belongs to the integer. And likewise, for any of the examples which you take any integer, and when you add those integer, it will give you an integer indeed. So is it satisfying the closed under addition? Yes, absolutely. But what about, is it closed under multiplication? Let's find out. Let us take alpha, which belongs to a real number, and let us take an integer which is z. Okay, so let us take alpha as 2. When you multiply that with z, and let us take z as 2, when you multiply alpha with z, you will get 2 times 2, that is 4. Is this integer? Yes, it is integer. It is fine. Okay, let us take another example wherein we will take alpha as 1 by 2 into 2. It will be 1. It is still fine. It is indeed an integer. But what will happen? Things will change when we will take alpha as pi. And when we multiply alpha, which is being taken as pi, with the z, we will get 2 times pi, which is 2 pi. Now things get interesting. Since this does not belong to integer and our scalar multiplication condition is dissatisfied, and hence we can say that the set of integers are not vector spaces. I hope I was clear to all of you, and all of the questions are being explained as simply as possible. I hope you guys enjoyed the video, and if so, make sure to like, share and subscribe this channel. Let's meet in the next video. Thank you.